Welcome to Brain Vision.
Okay, so we have a fairly challenging problem here. We have two wires that are both carrying current coming out of the page, and they carry the same current, 16.5 amps, and the two wires are 8.2 centimeters apart. So then we're told at a point that is 12 centimeters away from this first wire, I'll call that wire 1, and then 13 centimeters away from wire 2. At that point, we want to find the magnetic field. So there's really only two places that position can be. So it's going to make a triangle, either with this point being up here or kind of down off the screen here. So we'll do it up here. So that tells us then that this distance is 12 centimeters. And then this distance is 13 centimeters. And so what makes this kind of difficult is at this point, these two wires are making magnetic fields that are going in different directions. So what we're going to have to do is find the field that each wire produces separately, and then break that down into X and Y components, and then we can add them, and then find the magnitude, then find the angle. So to start, a helpful thing to notice is that if we think about the magnetic field that these wires are producing, so we know it's going to be in circles around each one. And so if I had drawn this a little bit better, you could see that along this line that's taking us from the wire up to point P here, where we're looking, the fields always intersect this at a right angle. So that should be a right angle everywhere. And so that tells us then that if we extended out these lines a little bit, then the field from wire 1, which I'll call B1, is going to be making a right angle right here with respect to that line. So that's a right angle. And then similar reasoning, field from wire 2, so B2 is going to be making a right angle along this line. So like that, with that being a right angle. So we have B1 and B2 here, both going at different angles. So we want to find these values and break them into components and add it all up. So to start, we can do the easy thing and just find what the absolute magnitude of each of these two fields are. So B1 is just the field from a long wire. So mu naught times I over 2 pi R1. And so using R1 here then as 12 centimeters and I as 16.5 amps, we should get that it is 2.75 times 10 to the minus fifth Teslas. And then doing the exact same thing for B2, mu naught I over 2 pi R2. Now with that as 13 centimeters, we will get 2.54 times 10 to the minus fifth Teslas. So now we need to do a little bit of geometry. So basically, if I draw an extra vertical line here, we want to find what this angle is, and that will help us break B1 into components. And then we want to find what this angle is for B2. So here, I'll draw these in. So we want to find that angle for theta 1, and then that angle for theta 2. And you could probably do this with a lot of different geometry techniques. Probably the easiest to do is to do the law of cosines here. And so it turns out that if we call this theta 1 and this theta 2, those are going to end up being these same angles up here, theta 1 and theta 2. And you can kind of see that by the fact if we look at one of these angles and rotate it 90 degrees counterclockwise, then you can see that's going to make this exact situation up here. So on the other hand, if we rotated this clockwise, we would be looking at something like this. And that's the exact situation we have down here. So everything up here is just rotated by 90 degrees. So those end up being the same angles. So we just want to find theta 1 and theta 2 then. So unfortunately, this isn't a right triangle, and so we have to use the law of cosines to do it, which is a little bit more complicated. But so that tells us for the angle that we're interested in, which we'll do theta 1 first, that the side opposite of theta 1, I'll call that side C, and then I'll call this side A and side B. It tells us that side C squared is going to equal side A squared plus side B squared, and then minus 2 times side A times side B, and then times cosine of theta 1, so times cosine of the angle across from side C. So we know C, A, and B, and so we can solve for theta then. So I won't go through all that algebra, but these are all just numbers, so we'll get cosine of theta equals some number, and then do inverse cosine of both sides. And so when we do that, we should get that theta 1 is equal to 77.6 degrees. And then we'll do the exact same thing for theta 2, or you could kind of do a bunch of filling in angles up here to figure it out as well. But in this case now, we'd be saying, now we're interested in this side, so we're saying side B squared should equal side A squared plus side C squared minus 2 AC cosine of theta 2. And we solve for theta 2, and we should get that it is 64.4 degrees. Okay, so now finally we have the magnitude of these two fields, and then we have the angle each one makes. So we want to now find the net field, and so we'll just do this in components right away. So we'll say B net in the x direction. So this is now just adding these two separate fields here. So in the x direction, we're just going to have, we can see it's going to be to the left, so it'll be a negative sign. So we'll have minus the magnitude of B1, and then usually we're either taking a cosine or a sine. Frequently we associate the x direction with cosines, but if we see how our angle theta is actually defined here, because it's kind of pointing in the vertical direction, it's actually going to end up flipped, and finding the horizontal component is going to be by taking the sine of this value. So really what we're doing is breaking it into a right triangle like this. And so for this angle, we take the opposite over hypotenuse, and that'll give us then this horizontal component of it. So minus B1 cosine of theta, or I'm sorry, adjacent over hypotenuse for that. So cosine of theta 1, and then similar thing for theta 2, that's also going to be a cosine, that's also in the negative direction for x here. So minus B2 cosine of theta 2. And so we have our values for B1, B2, we have our thetas, so we evaluate that, and we should get negative 49.75 times 10 to the minus 6 Teslas. And then for the y direction, we do the same thing. So usually if the x direction is cosine, the y direction is going to be sine. So those are almost always just the opposite of each other like that. So in this case, B1 is pointing, it's gotten a little bit messy over here now, but that's going to be pointing in the positive y direction if we look at that. So that will be B1 sine of theta 1, and then B2 is in the negative direction, so minus B2 sine of theta 2, and that was theta 1. And so we evaluate that, and we get negative 5.08 times 10 to the minus 6 Teslas. And so now we have the x and y components, and so we can get then just the net magnitude as square roots of b net x squared plus b net y squared. So just doing the Pythagorean theorem there. And that will come to be 5 times 10 to the minus 5th, 5.00 times 10 to the minus 5th Teslas. And they ask us to give this as a full vector, so probably then they want the angle as well that goes with this. So we can see the x component is negative 49.75 times 10 to the minus 6. So we have something like this. And then only minus 5 in the y direction. So maybe something like that. So here is our net field. Here's our y component. Here's our x component. So we'll find this angle here to define that. And so that angle should just be the inverse tangent of the opposite side. So that will be the magnitude of b net y. And then over the adjacent side, so the magnitude of b net x. And so that should come to be 5.83 degrees. And so as we've defined it here, we would say then the magnitude of this field is 5 times 10 to the minus 5th teslas, and its angle is 5.83 degrees below the negative x-axis.